Hi, good morning, good afternoon, and good evening. Thank you for joining us from 74 countries around the world at Graph Plus AI Summit. I'm your host, Vice President of Marketing at TigerGraph, Gaurav Deshpande. Let's quickly review today's agenda. We have an excellent, exciting day in store for you. As a part of general session today, we have multiple keynote speakers. I'll introduce those in just a moment. We will go over recap of the first day, multiple sessions and insights from it. We will share results of Web App Hackathon that we concluded recently. I'll also go over the day two's agenda and then finally introduce the two keynote speakers that we have. Let's go ahead and recap the first day. You can see the stellar group of people who presented yesterday from JP Morgan Chase, Jaguar Land Rover, Forrester Research, Intuit, Ippen Digital, Forbes Reporters, IBM, all the different partners, including Accenture, Mastic Infotrails, innovative startups like Sayari Labs, Infinity Analytics. We had people all the way from Ivory Coast, Yaya from Ivory Coast talking about COVID-19 tracing. We had amazing panel yesterday, amazing roundtable yesterday. We had multiple sessions yesterday. So if you did not get a chance to attend it, be sure to go back and attend those. We also had a wonderful session from John Snow Labs, our partner, which is working on combining natural language processing with graph technology for life sciences and healthcare industry. Be sure to check out those sessions in case you missed those. I'm going to go ahead and right now introduce a short video that we have built for you with the highlight reel. Thank you.
So I think the really big change that we came across, really in the first few days as the crisis hit, was that everyone was trying to say to us, what's the forecast, right? Tell me a forecast. What do I do, you clever AI people? What do I do? Tell me the forecast. And we had a go, and we realized within about 8 hours that the forecast was just rubbish, right? It's rubbish. There's no point. There's no point forecasting because there was no signal that you could make any sense out of, right? AI is not going to help you if there's just nothing to go on. And so what we pushed back on immediately was stop trying to use forecasts, right? AI is not going to tell you how to see the future, but it can tell you how to react to the present, right? And that was a massive change for us. And in fact, how we got involved in Graph, hate to bring it back to Graph, guys, right? But that's one of my things, is we were using the supply chain graph that we created to say, okay, so you can't see the future, but you can react really fast to every signal you see. So if you can't manufacture a wiring harness because all your 40% of your Serbian factory has gone into lockdown, right, which happened to us, right, then what do? Where can you get wiring harness from? What cars can you make given the things you already have? Given the things you already have, which markets are going to be the right place to send it? Given the markets that are open, which are the cars you should build and what cars you shouldn't build, right? Because if you build the wrong ones and it sits on a boat for 8 weeks and then doesn't sell, well, you've got a lot of working capital doing nothing. So, and that's actually carried on through, right? We're kind of in a new system where, yeah, we're going to get back to forecast, but we're never going to be in that kind of tell me what's going to happen over the next 6 months and we'll just sell our factories as if we know the future. It's never going to happen again. We're going to be thinking about how we use this stuff to adjust all the time to the signals coming in. And I think that's a really good thing because that's true digital behavior.
Algorithms get all of the press, but it's all about data that leads to AI success. So, we hear about AI, and AI every day, I guess, right? AI machine learning is every day. But what about data, right? Without data, applications don't run. Without data, AI doesn't run, right? and if your data isn't really integrated and having contextualization, then, well, all of these AI processes, your application processes will not going to run, right? As more efficiently, but also not drive value to the business.
Knowledge graph, which by design is symbolic AI with machine learning. It used to be the case, two camps is fight against each other, but now it's the time we need to connect them together. And knowledge graph is a great media to connect to. Think about, knowledge graph can start with human curated knowledge, but can be augmented by machine learned knowledge. And then becomes a virtuous cycle to keep expanding the knowledge, keep connecting the dots. And for you to run a lot of different algorithms mining, sometimes directly on the graph. You don't even need to go for a pipeline, right? That's the power, how you can build a knowledge graph. The more knowledge you have in the graph, the more you can do for everybody.
At a high level, graphs clarify relationships. Others might say that they provide more nuanced insights. Put simply, relying upon entire paths or sets of relationships in a graph can provide deeper insights than just looking at nearest neighbors, which is what a typical database would afford you. In a sense, you can think of turning an initial hairball on the left into nuanced insights like which portions of my graph, whether it's your supply chain, customers, etc., are things like low risk or high risk. Then machine learning can leverage those insights, right, and turn those more nuanced inputs into better models.
Well, welcome back. I hope you enjoyed that highlight reel. Let me recap some of the interesting things in there. So Harry Powell, as a part of the Digital Transformation Roundtable yesterday, mentioned something that opened my eyes, and I'm sure there'll be interesting insights for you also. He said when COVID-19 pandemic hit, suddenly, overnight, forecasts were useless. AI cannot predict future when the things are changing so rapidly. Graphs are essential in understanding new signals, especially as they're pouring in, changes in demand and supply in case of Jaguar Land Rover, and adjust quickly. Graphs can help improve AI by processing signals faster. The second insight that I want to share with you is from Noel Johanna, who is the Vice President, Principal Analyst at Forrester Research. He had the best quote from one of the generalization slides that he had. Algorithms get all the praise, but it's all about the data that leads to the AI success. And there's nothing truer than that, because graphs are the one to connect all data sets and pipelines to enable that success for AI. He also shared a wonderful examples. One of the examples that he shared was ML, or machine learning, can predict customers who are likely to churn, but graph and AI together can determine the best way to retain customers and improve the customer experience. So graph essentially makes AI better. Last insight that I have from you is Dr. J.U. from Intuit. As a part of the Digital Transformation Roundtable, he shared an example of using knowledge graph. He said, we need knowledge graphs to make right connections. At Intuit, they use knowledge graphs for AI to do matchmaking, essentially matching up their customers with the right tax experts. So the more knowledge you pour inside a graph, the more you can do for everybody, including your customers. So with that, let me hand it over to, and switch over to recap from Brad Spire's session, the Executive Director at JP Morgan Chase, who made two very clear points yesterday. He said graphs clarify relationships, and because of the nature of the graph algorithms, because of the exponential growth, you require scalable software. The first point that he made was graphs clarify relationship. To put it simply, relying on the entire paths or sets of relationships that a graph can provide can give more meaningful and deeper insight than just looking at the nearest neighbors. So which is what a typical database just looks at, the nearest neighbors that you have and tries to get insights out of that. Graph goes much deeper in relationships. He also talked about a very nice metaphor for how the data is currently and how it is with graph. So he says, you can take all that hairball of data and connections and turn that into actually nuanced insights that you can use for business making, for business decision making, and use the portions of the graph where you can see your supply chain or customers are at high risk or low risk for a particular type of condition. So for example, customers churning or supply chain that's likely to run out of parts. Those are the things you can see clearly with graphs. You can take hairball of data and turn that into nuanced insight. He also talked about how machine learning can leverage these nuanced insights, deeper insights, and have better inputs to turn into better models for AI. Again, bringing it to the fact that AI and machine learning are helped with graph in terms of improved accuracy and efficiency. The last thing he shared, and it was his parting thought yesterday, was graph algorithms scale exponentially, which means graph, by definition, requires scalable software more than any other situations or challenges that you have considered in the past. So his advice is, whichever software you look at, make sure it's a scalable one. Thanks a lot for sharing your insights, Brad. That was wonderful. With that, let me hand it off to John Herkey, Developer Relations Leader at Tigergraph, to cover the results of Web App Hackathon and share some of the projects with you. Take it away, John.
Hi, my name is John Herkey. Thank you so much for being here today at the Graph Plus AI Summit. I'm the manager of the developer relations team, and I'm here to give you a few updates about the things that are going on in the community. So we just wrapped up the Web App Hackathon. We had 200 participants from 32 different countries and $15,000 worth of prizes. This was a co-hosted event by Streamlit and Graphistry. And so our communities came together and engaged our communities to learn about these new technologies. The challenge was really about building an application using Streamlit, and you could use Graphistry and other visualization packages to create an application of your choice. So this could be anything from a dashboard to an application that interacted with TigerGraph. So I want to go over some of our Web App Hackathon winners. In first place, we had Graph Shortest Path and Centrality-Based Airport Dataset Project. This was by Xi and Lin Shu. What they created was a dashboard that illustrated the shortest path between two different airports. They used a suite of technologies, including React, and integrating that with Streamlit, which is based in Python. They also created a multi-map that showed you the difference between the different algorithms. And so all in one application, you could see all these differences. And if you are curious about the project, they're actually going to be presenting later on in this Graph Plus AI Summit. In second place, we had TigerStream. TigerStream created a dashboard on the movie dataset. And so the movie dataset has the users and what movies they watched and recommendations. And what he put together was a user profile, and the user profile then had attributes about the different users, and then had some Plotly and visualization components that actually illustrated the connections between the different attributes. And that was by Kaushal. And then third place, we had TigerGraph Visualization Query Tool. So this one was a little bit different than the other two winners. It wasn't a dashboard based off a starter kit, but it was a tool that you could use with any of the starter kits to interact with that starter kit and actually query your database and get that data back in a JSON format or tabular format. And that was by Jesse. Lastly, what we want to do is introduce you to our developer forum and developer chat. If you're not familiar with the developer forum, this is a great place for you to go and ask questions. It's a Q&A sort of style. You can simply go into community.tigergraph.com and you can see all of the different questions that have been asked in the community so far. So if you run into any blockers during your project, maybe you're trying to figure out how to use UDFs, maybe you're trying to figure out how to incorporate accumulators into your queries, one thing you can do is go to community.tigergraph.com, click on the search button, and then try to find the answer there. And if you can't find the answer, feel free to just create a new topic. If you create a new topic, then you can give it a title, tag it, and one of the community members or TigerGraph staff will see that new topic that came up. And we're always in the community willing to help and looking forward to being able to work with you. And then lastly, we have the developer chat. So the developer chat's a great way to stay connected with all the developers across the world. So unlike the forum where it's more of a question and answer, the developer chat just allows you to talk with individual developers or the community. And so you can see some of the projects that other developers are doing. Maybe other developers are creating new blogs. There might be events or announcements that come out. You might see developers jump into the things called project rooms, and the project rooms allow you to do video sharing and speaking with other developers. So there will be code development sessions. In the mornings at 8:15 Central Time, we have a developer chat with the developer relations, and you can jump in if you have a project. The developer relations team is more than willing to always help you out and get through any barriers that you might have. And so with that, I'm going to pass it on, and thank you so much for being here at the Graph Plus AI Summit.
Thank you, John. That's an amazing group of young people that are doing amazing things with graph combined with machine learning. I wish I was that smart when I was that age. With that, let me go ahead and review day 2 agenda quickly with you. We are right now in the general session. These are the opening day remarks. And after that, following that, we have 2 wonderful keynotes for you. Dr. Yul Leskovich, Chief Scientist at Pinterest, Professor at Stanford. He's going to share thoughts on what is the next thing for AI and graph. And then we have a keynote from Danny Clark, Head of Fraud Strategy at New Day. He's going to talk about fraud detection in the cloud with graph and AI. Following that, we have 2 exciting executive roundtables for you. So stay tuned with us for that. The first one is around graph query languages. This is something that Dr. Yushu mentioned in his keynote yesterday. GQL, or graph query language, is the ISO initiative around establishing a standardized graph query language. And we have a panel of industry players that are shaping that graph query language as a part of that particular panel. Following that, we have hardware accelerated graphs, which is where Intel, Dell, and Xilinx, the three leaders shaping the hardware accelerated graphs for analytics and machine learning. They're working on creating hardware that's 10 to 100 times faster for analytics and machine learning with graphs. Following that, we have multiple technical breakout tracks. There are a couple that I'll review first. The first one is Graph plus AI in the cloud. Again, if you are looking at deploying graph combined with machine learning or graph solutions by themselves in the cloud, don't miss this track. There are two amazing speakers from AWS that I want to single out. Jack Secord, who leads the analytics at AWS, is speaking with Emalu, who is the product manager for TigerGraph Cloud, and Duke, who leads the team for TigerGraph Cloud. They are delivering a session on how TigerGraph Cloud is used with AWS to power the scalable graph database as a service. TigerGraph Cloud is our graph database as a service. The second session that I want to point out in the Graph plus AI in the cloud is from Phi Wen. Phi Wen is an AI and machine learning architect at AWS. He's talking about how to build the next generation graph and machine learning solutions using Graph, TigerGraph Cloud specifically, and Amazon SageMaker. So if you are looking at combining AI machine learning solutions with Graph in the cloud, you definitely don't want to miss these two sessions. And of course, there's an introductory session to TigerGraph Cloud for those of you who are interested in that. Following that, we have an exciting track because you mentioned during last year's conference that NLP, natural language processing, was one of the main topics of interest for you. So we combine NLP with Graph, and we have a track for you for combining NLP with Graph for analytics and AI. 3 excellent sessions there. We have the first session with John Snow Labs, a partner that's talking about combining NLP, the Spark-based NLP library, with Graph for healthcare and life sciences. That's an industry-specific session. So if you are in healthcare and life sciences, it's of interest to you. The second session in that is about semantic graphs, building those from medical documents, which is where Akash Kohl, who's part of developer relationship at TigerGraph and a university student, has built an amazing solution for semantic graph from medical documents. The last session is about Rasa tool. If you are not familiar with it, you should definitely be. It's a wonderful open source tool, and it's about integrating the Rasa pipeline with Graph. With that, let me go ahead and review rest of the sessions. There are 3 more tracks that are there on day 2. Enterprise ecosystem for Graph plus AI. I'm really, really excited about this because we have Intel's Director of AI and High Performance Computing, Dr. Nikhil Deshpande, presenting their solution, how they are taking performance of analytics and machine learning in Intel 10 to 100 times faster than what it is currently. Anurag Juneja is from Dell. He's going to do a session on how Dell servers are being used in the healthcare domain with TigerGraph specifically. Lastly, we have sessions on containerization of graph solutions, specifically containerization related to Amazon Elastic Kubernetes Service and Google Kubernetes Engine. We also have a session on Snowflake Cloud Data Warehouse and Graph integration. So you remember that Dr. Yushu mentioned that yesterday in general session during his opening remarks. We have that session, and you can see a live demonstration of that solution. And last session in that particular track is no-code machine learning pipeline. Again, this is something that I'm really, really excited about because no-code combined with machine learning has the potential to unlock graph and machine learning both for audiences that do not want to or do not write code currently. So for the business users, for business analysts, this is a wonderful session. You should definitely attend it. Following that, in parallel with that, we also have a visualization track. So you told us as a part of last year's conference that you wanted to hear more about how to visualize the graph data using both open source tools as well as commercial tools. So we are bringing you a session with Tableau. This is something that Dr. Yushu mentioned in yesterday's general session remarks, how to connect Tableau up with the graph solution, and we have a live demonstration of that as well. And then we have a couple of sessions from the Web App Hackathon Winners that are following that. The last track is data science with graph algorithms and machine learning. And even though it's a last track that I want to talk about, it's one of the best tracks. Here we have Dr. Arvind Sathi, Director of AI Literacy from KPMG, talking about trends and opportunities for graph-based AI. We also have machine learning for fraud detection, where Xinyu Chang and Nalu Chu from Tiger Graph Developer Relations are going to present specifically machine learning feature sets for credit card fraud detection and a couple of other fraud detection types. So if you are in banking insurance industry, or if you are in technology industry and you are worried about incentive fraud, definitely should make your way into that particular session. We have a wonderful session on e-commerce and how you can build better recommendation engines with graph and machine learning. We have an excellent session with Graham Gansel. Special shout out to Graham. He's part of our partner Expero, who is actually bringing forth experience of working with largest banks in the world, largest insurance companies in the world, largest fintechs in the world on how to fight financial crimes, a deep dive into that. And then last session we have for data science with graph algorithms and machine learning track is a data lineage, which is a topic of immense interest for all of you. With that introduction of rest of the chart, let's go ahead and make sure that you stay with us and come back tomorrow for day 3, where we roll up our sleeves and get hands-on with graph and machine learning. There are 3 sessions, live workshops for you to pick from. Capacity is limited for these workshops and by design, because we want to ensure optimal learning experience from you. So before you sign off today, please sign up for the workshop that you want, because they will get filled up and we don't want to have to turn you away. There are 3 sessions, 3 workshops. The first one at 7 a.m. US Pacific or California time is doubling the performance of your fraud detection with graph and machine learning. We'll actually show you how to build a system that can double the current performance of your fraud detection system with graph and machine learning. The second live workshop after that is how in 90 minutes, if you don't know anything about analytics and machine learning, it's perfectly fine. Come to this workshop. We'll show you how to start doing analytics and machine learning using Tiger Graph Cloud in just 90 minutes. The last one there is all about recommendation engines, about e-commerce. How do you build the next generation e-commerce solution with graph and machine learning? So those are the 3 workshops. Please stay with us for those on day 3. Following this, now let me introduce the 2 keynote speakers that I'm super excited about. Danny Clark is the head of fraud strategy at NewDay. Danny will share how NewDay identifies and prevents fraudsters from joining their network faster than ever before by using graph and machine learning in the cloud to check data against known and new fraud syndicates. So that's a wonderful session for those of you who are working on fraud. Definitely join, stay on, and listen to Danny share his insights related to that. Now let me introduce the first keynote speaker of the day. Today's first keynote speaker is Dr. Yur Leskovich. He's the chief scientist at Pinterest. He's a professor at Stanford University. He's somebody who's well-known inside AI and machine learning, both on the commercial side of the house because of his Pinterest responsibilities, and also very well-known in the academic circle. So it's my privilege and honor to hand it off to Yur to cover what's next in terms of evolution of graph for delivering the next generation AI. Take it away, Yur.
Thank you very much, Gurav. I would appreciate if I could share the screen and the video. Okay, maybe no video, just the screen. Can everyone hear me?
We can hear you really well.
Super. So I'm very excited to speak to you today. And what I'll talk about is how do we bring the power of deep learning to relational data? How do we bring power of deep learning to graphs? And really, like I share my time between Stanford University and Pinterest. And especially at Stanford, we see a lot of companies, commercial entities, a lot of use cases that are kind of next generation use cases that perhaps the today's technology is not able to solve. And through that, and through those industrial partnerships that I'll talk about, we at Stanford actually go and build the technology that is next generation technology that solve those problems. And the topic of my talk today and what I want to show to you is one such example of where we think the graph analytics, graph machine learning is going, and what is really the next generation technology that is going to power this. So as the topic of this gathering is, graphs and networks are all around us. And by this, I don't only mean, you know, traditional kind of social networks and so on, but also there is a lot of relational data that can naturally be modeled as graphs. Even if you think about software is a graph. If you think about molecules, molecules are connections, friendships between atoms, and those can be captured as a graph. Various kinds of communication, transaction networks. If you think about biology, brain, how our bodies work, it's all about entities, relations between different biological entities, for example, genes, proteins, drugs, diseases, and it's all about the relationships between these entities. And all these areas can be basically modeled, or all these domains can be modeled as graphs. So the number of applications for graphs, and in particular for relational data and for deep learning on top of relational data, goes everywhere from computer graphics to robotics, autonomous driving, medicine, drug design. Also, as I will show in this talk, there are large use cases in recommender systems, physics-based simulations, fake news detection, drug repurposing, as well as chemistry. And the beauty of graphs is that they are a common language, right? They provide us a way to model these rich, complex domains that can be very different, come from different areas, but at the end, the underlying mathematical representation, the representation over which we learn, is the same. So this is the beauty. And as I mentioned in my group, we work with a lot of different industrial partners, and we really try to understand what are kind of the problems that are coming up for them, what are the challenges where they are hitting the wall, what are basically things that are too hard, too undefined, too risky for them to solve, so that together with our super bright students, we can attack these problems, iterate on them quickly, and come up with solutions. And what we see in machine learning tasks related to with graph-related data is that essentially we can break them into, let's say, 3 different classes. We can think of them as node-level prediction tasks, where we are trying to predict some property of a node, perhaps whether the user is going to churn. We talk about link level prediction tasks, which, for example, would be try to predict whether a given financial transaction is fraudulent, or perhaps do a graph or a subgraph level prediction task, where the idea would be to, for example, identify a money laundering ring, or some other graph level prediction task. For example, predict whether a given molecule is toxic or not, where the entire molecule can be basically represented as a little graph of bonds between atoms. And one example of the task to be more concrete is that we are given, for example, a partially observed or partially labeled graph, where for some nodes we know their type, we know their color, and we want to predict or infer the type or the color of other nodes in the network. And what is a type? The type would be like, is the user going to churn and drop from my network? For example, if I'm a telecommunication company. Perhaps if I'm a healthcare provider, I could say, given the measurements and the history I know about this patient, what is the disease of the patient, or how is the disease going to progress? Or, for example, if I'm a computational biologist or a drug company, I would want to say, what are the functions of this protein? What other proteins does this protein interact with? And all these types of tasks, basically, we will be able to solve with the technology I'm going to present. But if we look at the machine learning life cycle today, we are first given, for example, the graph data. Then we go and spend a lot of time. Data scientists are spending endless hours coming up with node features, coming up with ways to compute shortest paths, to compute PageRank scores, clustering coefficients, degrees, second degree neighbors, a lot of different things. And it's really just kind of this endless cycle of this feature, that feature, another model every single time, right? And only then, once all this kind of hard work of feature engineering has been done, the machine learning algorithm is able to be applied. and then, we get the model, we get the predictions. But it is really this kind of endless struggle of generating the right features, taking huge amounts of time, taking complex queries, and a lot of manual handwork. And really, this feature engineering is today what is the biggest, what we see is the biggest bottleneck in especially graph machine learning, because the possible number of features or the ways to describe the network structure is humongous. So what we would like to do is to say, can we go away from feature engineering? Can we save the data scientists all the time? They need to be coming up with these features that are suboptimal, heuristic, hand-engineered, complex to maintain. They get out of date very quickly. They get corrupted very quickly. They may be very kind of finicky, very non-robust. So how could we just do the feature generation, feature learning automatically for free by these machine learning methods? And when I say feature engineering, right, I mean features for all kinds of tasks, for tasks at the level of nodes, for tasks at the level of link prediction, so predicting interactions between pairs of nodes, or perhaps for classifying entire graphs or entire features for entire graphs or entire subgraphs. And as we talk to the data scientists, we see basically two major pain points. First major pain point is that data scientists have to hand encode features to solve prediction problems. And features, of course, are task specific, and hand encoding these graph features is very complex and involves expensive graph queries. It involves exponential expensive graph queries. It is, as I mentioned, it is very error prone because the underlying data graph may change over time. The features may become obsolete, and things may not work anymore. It is very suboptimal because we don't know what features we haven't yet tried out or what signals we haven't yet thought about. So we don't know how well our model is really doing, or how away we are kind of from this optimal model. And of course, it is super labor intensive. It takes a long time for a data scientist to kind of ramp up to have enough domain knowledge that they can start thinking about the domain and thinking about the features they are generating. And of course, when people move and leave, a lot of knowledge is taken away from the team. So this is kind of really non-scalable. It's very expensive, very inefficient, both computationally as well as from the people side of things. Another pain point we see, which is especially true with the graph data, is that the graph data is often incomplete, right? Address books are incomplete, social networks are incomplete, lists of interests of users or profiles are incomplete, protein interactions in biology are incomplete and needs to be discovered. Ancestry relationships are incomplete. When we see customers, we only see them on our platform for a short period of time, but there is other things customers are doing that we don't get to see. So data is notoriously incomplete. Entity information is also incomplete, right? Many times we don't have all the information about a given entity. But, right, the predictions we are making often entail completing the missing information. So, right, and what this means is that in this way, leveraging the relational structure is even so much harder because it is incomplete. It is very hard to scale algorithms to reason about the relational structure, right? But if you make a step back and say, why do we have to be doing all this? Because the AI, the field of machine learning, is in the middle of a big revolution, right? And the big revolution is called the deep learning revolution, and especially in image computer vision, in natural language processing, it was the neural networks, the convolutional neural network architecture, the transformer architecture that really led to this revolution, to this superhuman performance on many important machine learning tasks. And we see these huge reductions of the error over time. And if you look at the core and say, okay, so what is the core innovation? What is the core that allows us to get to this revolution? It's really called representation learning. And here I give you an example from computer vision. Right, in the old school computer vision, the way algorithms operated is that first you took the image and then you built some hand-engineered feature detector. So basically, you said, "Let me describe this image with a set of features." For example, one such feature descriptors were called SIFT features, where basically you took this image and represented it as a set of features, so that then you would be able to apply your favorite machine learning algorithm classifier to it to, for example, predict what's the object on the image. And what we are doing in the graph machine learning today, it's essentially the same. We take the graph, we spend a lot of time designing the features so we can then develop the classifier. But the power of deep learning, the power of neural networks is that I can just point my neural network to the raw data, and in an end-to-end driven way, this neural network will learn what are the useful features of the image, what are the useful signals, and how to combine them to give me the end prediction or the end result. So this is what we'd like to do. No more hand feature engineering. But the question is, how do we bring this to graphs? And if you look at the state of the art today, deep learning has made breakthroughs in text, in speech processing, and in computer vision. And if you look at it, these are what I would argue are simple data types, right? The modern deep learning toolbox is designed for simple data types. Text is a simple linear sequence. Audio is a simple linear sequence, and images are fixed size grids. They basically can all be resized to have the same size. They are all the same shape. Images as well as the text has some spatial locality. It has a left and a right, up and a down. So it's very simple type of data. But if you look at the graphs are much more complex, right? They can be of different sizes. They have different types of relationships. So the big question becomes, how do we develop neural networks that are much, much more broadly applicable? How do we develop neural networks that can be applied to these complex data types, right? And we see graphs, relational data, as the next frontier of deep learning. So this is what we are really excited about. And this is really about how do we bring the power of deep learning to complex data like graphs. And this is really the core of the research that my research group at the computer science department at Stanford is working on. So what is the goal? The goal is to do representation learning on complex data, where basically what we'd like to do is we'd like to take the input graph, the input relational structure, be it as complex as it is and as heterogeneous and dynamic and so on, and directly apply a neural network to it so that we can learn the representation, the feature representation, the embedding of the nodes, of the links, of the entire graph, so that we can then readily apply machine learning to it. So we don't want to do this step by hand, which is what is happening today by manual feature engineering. We want the power of deep learning to do this for us, in some sense, for free. So conceptually, what we'd like to do is we'd like to design deep neural networks that will take the graph as an input on the left, pass it through a series of nonlinear transformations to give me accurate predictions on the other end. And when I say accurate predictions, I really want to be agnostic. Maybe I'm predicting node labels. Maybe I'm detecting fraudulent links. Maybe I'm classifying molecules, whether they are toxic or not. All these tasks will be able to be solved with this type of deep learning approach and architecture. So, why is this hard? The reason why this is hard and non-trivial is because networks are notoriously complex. They have arbitrary size and they have complex topological structure. They also have no spatial locality like grids or so images or linear sequences like text have, right? There's no reference point. There's no up, down, left, right. And we don't know, or it's impossible to resize all networks to have the same size as images do, right? And what is more important, these networks are heterogeneous. Many times they are dynamic and they have a lot of additional signals, features, profiles attached to the nodes and the edges of this network. So the question is, how do we generalize deep learning to graphs? And my group at Stanford has been at the forefront of this exciting new area in machine learning, in artificial intelligence. And the key idea, the key insight that allows us to do this is to interpret the underlying input graph, the underlying network, as a computation graph, right? And what this means is that now we can learn how to propagate and aggregate information across the underlying graph structure, right? And one way to look at this systems is to say, if I want to make a prediction about node A, I can take all the information I have about this node, but I can also learn how to take information from some of the key neighbors of this node and aggregate it, and this way increase the description, what I know about the red node here in the center, to be able to do better predictions. And not only I can take information from neighbors, I can also take it from neighbors of neighbors. And this means I can go very far in the graph, collect all the information, aggregate it, create features out of it, to be able to make accurate predictions. And we see that this leads really to state-of-the-art and increases the performance of machine learning methods on graphs by double-digit percentage points, and many times even more. And the key insight, as I said, is to say, if I have some abstract input graph and I want to make, let's say, a prediction for this target node A, then the structure of the neural network that allows me to do this is depicted here, where basically each node gets to define its own neural network structure, where it takes information from its neighbors, here B, C, and D, transforms and aggregates it. And each of these other neighbors takes information from its own neighbors. For example, B takes information from nodes A and C, and here is the structure of the network. While the node C has 4 other neighbors, so it's going to take information from 4 other ones. And here we can account for directionality of the nodes and edges. We can account for the features on nodes and edges, for the types of relationships between nodes and edges, and so on. And the point is that actually here in these aggregation functions, in these data transformation functions, there will be little neural networks that will learn how to optimally combine this information from neighbors and neighbors of neighbors to make an accurate prediction for a given node. Why is this different than traditional deep learning? This is different because we are not learning over one fixed graph, over one fixed neural network architecture, but every node gets to define its own neural network architecture. For example, the blue node here has a very skinny neural network because it has kind of low degree nodes around it, while the node C here has a very different neural network structure, much bigger fan out neural network structure. So we are basically learning simultaneously over millions or billions over different neural network structures or architectures. And what are some key benefits of this technology? First, there is no manual feature engineering needed. There is end-to-end learning results in optimal features. And basically, we can do this for any graph machine learning task, for node level, link level, subgraph level. And as I will show you in the rest of my talk, we can scale this to billion node graphs. So we can really, this is ready for industrial applications, as I'm going to illustrate. So what I want to do in the remaining 10 minutes, I want to talk about some applications of this technology, of this GraphSAGE technology we have developed at Stanford. And I'm just going to highlight 2 of them, and there is many more that I'm not able to touch in this short talk, but please send me email, very happy to talk about them as well. So first is around computational drug discovery, and basically doing what we call drug side effect prediction. So imagine the following, right? Today, many patients take multiple drugs to treat complex or coexisting diseases. In the United States, basically half of the people over 70 are simultaneously taking 5 or more drugs. And the problem is that in drug trials, we test the safety of each drug individually. But the problem becomes when people take multiple drugs together, there might be adverse side effects, which leads to basically there might be interactions between drugs, which leads to additional adverse side effects, maybe heart disease, maybe, I know, some depression or something like that. So the question is, how do we build a machine learning tool that will allow us to predict for drug combinations what kind of side effects may happen? And we do this through the graph heterogeneous graph and this type of GraphSAGE approach, where we are creating a heterogeneous graph where triangles are different drug nodes, and drug nodes are connected with different edges, where edge is the known side effect between two drugs. So basically, the idea is if you take drugs C and D, then you have the side effect R2, let's say nausea. But if you take drugs, let's say C and S, then you get three side effects, nausea plus two more, R3 and R4. And then we also know how drugs operate. So we know how they interact with the proteins in our bodies. So basically what we have is a second type of a node, which is the circular protein node. And we connect drugs to the proteins they target, and proteins interact with each other. So there's a network in the lower layer as well. And we can then, just using this data and using some of the known side effects, we can basically point our machine learning tool to this data. No human feature engineering needed. No need to select features, engineer them, run your models. Just point the neural network to it and press a button, train. And if we do this, basically what we are training our model to do is to predict links between these drugs. Basically say, for every pair of drugs, predict the link and the type of the link, right? What kind of side effects you may observe. And this is a multi-graph because there might be multiple different types of links between a pair of nodes. And what we find out is, for example, that this approach gives us almost like 40% better predictive accuracy than traditional approaches that are based on matrix factorization or feature engineering. What we also see is that this approach allows us to discover new, so far unknown drug side effects between different drugs. And actually here are the top 10 predictions by our model of what are the pairs of drugs and what kind of side effects they may predict. And we actually are working with medical doctors right now to evaluate them. And for 5 out of these 10 that were unknown, we were already able to confirm them. And as I mentioned, now we work on clinical validation with both hospitals in the Boston area as well as here at Stanford to basically identify novel side effects, which then doctors can be made aware of and not prescribe those pairs of drugs anymore. So this is the first method that predicts side effects of drug pairs, even for drug combinations, that has not yet ever been used in patients. So that's the first use case I want to share with you. And the second use case I want to share with you is around recommender systems. And this is really the recommender system that we built at Pinterest, and today is is recommending both the organic contents as well as the ads to hundreds of millions of users at Pinterest. I think it's making about 500,000 recommendations a second. And it is the default signal that is used all across Pinterest. And it is based on this graph-based technology. So Pinterest is a website. This is now a couple of months old, but I think the number of users is around 500 million now. And the number of pins, I think, is double what I have here. And the number of boards is also much bigger. But essentially, it's a website where people take images called pins and they create collections called boards and save these pins into collections. And this is really like a search engine for ideas, right? People would say, oh, I'm very inspired by this image, and maybe I'm an architect, so I have a board named blue accents, and I'm kind of saving images that have a blue accent, a blue item in them, because I use this for my professional projects. Maybe somebody else is saying, oh, I'm renovating my kitchen and I really like this vintage kitchen style, so let me save this picture into my vintage kitchen collection. And maybe somebody else is like, oh, I'm really thinking for good fireplace ideas, and I like this fireplace here, so I'll save it to my fireplace idea board, right? This is what people do. And the system we built at Pinterest is called PinSAGE, that uses this graph convolutional neural network, the GraphSAGE architecture, to basically generate embeddings of nodes in a large-scale Pinterest graph that contains tens of billions of objects. And the key idea is to borrow information from nearby nodes so that we enrich their description. it turns out, for example, that raw computer vision algorithms many times make silly mistakes because objects look alike. For example, the computer vision tends to confuse the garden fence with a bed rail because they look alike, or it confuses soil with ground meat because they look alike. And the goal here is to basically create better pin embeddings, better image embeddings, so that they can be used in any kind of classification, ranking, recommendation task later on downstream. And the key insight is that the way we want to build this system is to say, I want to have this signal to say, I want to predict what is related and what is not related. And I want to automatically learn embeddings, here denoted by Z, which is basically a feature representation for every pin, so that pins that are related, the distance between them in this embedding space is smaller than the distance between pins that are not related, right? So the two cakes should be embedded closer together than the cake and the sweater. And where does the graph come in? The graph comes in because we can think of these pins belonging to these boards, right? And the same pin can belong to different boards. But when we are creating the feature representation for the pin, we are not only using the information about the pin itself, but we unroll this network around it and get the information from the nearby pins as well and aggregate it. So basically what this will be is that this cake will learn that it belongs to the board with other cakes. And the cake will say, oh yes, I'm truly a cake. While this sweater will be in boards with other sweaters, and it will say, aha, I know that I'm a sweater, and I know how I relate to my other sweaters, and I know I'm very different from the cake. And this leads to amazingly accurate recommendations. For example, here is a pin for which we say, let's make some recommendations. Is some, let's say, California loggers cutting down a big tree. If you do based on visual similarity, you will make like silly mistakes about this kind of historical images of farmers and soldiers. If you do it based on textual signal, you will know that this is about logging, but it's kind of off topic. It's very different. But if you use our approach, you essentially see that we get great results. We get historical images of people cutting down big trees. Or another example, here is a picture of a cat with a funny hat. If you do based on the computer vision embedding, you get a lot of noisy results. If you include this graph information, this PinSAGE embedding, you can see how basically we get cats with funny hats all over perfect recommendations, right? And the last thing I want to mention is that these types of technology generalizes to making complex predictions in heterogeneous knowledge graphs, where we can basically take different types of entities, different types of relationships, and combine them into what we call a knowledge graph. Here is, for example, a knowledge graph for biomedicine about drugs, diseases, proteins, as well as adverse events. And you see different types of nodes, different types of relations. And what is the problem we can solve is that we can make complex predictions in these knowledge graphs. For example, a chemist may want to say, predict me what drugs C are likely to target proteins P associated with my diseases of interest D1 and D2. And we can learn this kind of ad hoc queries and this kind of predictions by basically navigating and learning how to move in the embedding space. So basically we can take our knowledge, encode it using neural networks in the embedding space. So when an arbitrary predictive query comes, very complex like here, and our system has never seen it, we are able to execute it directly in the embedding space and find answers. And this is extremely powerful because it allows us to answer arbitrary predictive queries that we haven't even trained on, we have never asked for, we have no training data for. So it's really about how do we transfer the knowledge from one task to another task without any prior training data about it. And our approach allows us to do this. I'll skip the details and I'll just quickly conclude. Right? So this technology that basically GraphSAGE technology that allows us to bring the power of deep learning to graph and relational data allows us to now apply deep neural networks much more broadly. It allows us basically to go beyond the frontier of classic neural networks to images and text and really apply them to complex heterogeneous data. It is also important because it brings the power of deep learning to relational data so that no manual feature engineering is necessary anymore, and really end-to-end learning is possible. We can apply this to many different tasks, as I said, at the node level, link level, subgraph level, as well as the entire graph level. And to summarize, GraphSAGE brings the power of deep learning to graphs. It fuses node feature information and graph information to provide state-of-the-art accuracy for graph machine learning tasks. Model size is independent of the graph size. This means our methods scale to billions of nodes, tens of billions of nodes. At Pinterest, it is scaled to entire Pinterest graph running in production, making recommendations as we speak. And it leads to significant performance gains over previous approaches. We see that, machine learning companies across the Silicon Valley are adopting this as well. I know Uber is using this super successfully. LinkedIn has invested a lot of resources in basically taking GraphSAGE, putting it in production to great success. And there are many other examples I can talk about. But really, the results in the research community in the past 2-3 years have shown that representation learning paradigm can be extended to graphs, that no feature engineering is necessary, and that we can effectively combine node attribute feature data with the network information, which leads to state-of-the-art results in a wide variety of domains and tasks. And this end-to-end training that is allowed by deep neural networks, instead of this kind of hand-tuned multi-stage approaches, leads to much, much better performance. So with this, I am done with my talk. Thank you very much. And I think I'll be available to take some questions later.
Yeah, Dr. Leskovich, there are a lot of questions, and I encourage everybody to use Q&A feature to ask more questions. I will ask all of them, I promise, in the roundtable that's following the keynotes. With that, let me hand it off to Danny Clark from New Day to cover fraud detection at scale. And I promise all the questions that you tee up, I will ask them of Dr. Leskovich and of Danny. And then we have a surprise third keynote speaker after Danny. I'll announce that shortly. So with that, let me hand it off to Danny.
Hello, my name is Danny Clark, and I'm the Head of Fraud Prevention at New Day in the UK. I've been with New Day in this position for almost 9 years and have experienced significant growth in my time with the company. My primary role at New Day is to manage fraud losses, minimising the fraud loss for the company while balancing the customer experience through all of the customer journeys. I've worked in financial services for over 30 years, working for a number of major UK and US banks, primarily in fraud and credit risk roles. I'm delighted TigerGraph asked me to present at this summit so that I can share some insight on what we do at New Day and how TigerGraph has helped us to be more efficient and effective in our management of fraud. So before I start, let me provide you with some background on New Day. New Day are a UK-based credit card and point-of-sale finance business with a heritage in full spectrum underwriting, from near prime to prime portfolios, in partnership of which I will come on to shortly. We're a digital, brand agnostic and scalable business. We have an in-house digital development and customer experience team who continue to push the boundaries to drive innovation and create best-in-class customer journeys. We are a trusted partner with some of the most exciting brands in the UK, including Amazon, AO, and Argos. The New Day Customer Manifesto guides us in helping people move forward with credit, and that's the manifesto by which we all live by. As I mentioned in my opening slides, New Day has experienced significant growth since the time I joined, and we are serving almost 5 million customers. This equates to the following statistics in 2020. 5 billion of spend through our products. This equates to over 10 million transactions per month. 19% of UK credit cards were issued by NewDay in 2020. 84% of active customers registered for e-servicing, allowing customers to interact with us online or through our app, offering many of our services which traditionally would have only been achievable through customer contact centre. 900,000 new customers were responsibly said yes to in 2020, and over 100 million customer service interactions in the year. A significant amount of data with a significant amount of insight. Here are some examples of the products we offer at NewDay. Aqua was NewDay's first product, issued back in 2002, focused at near-prime lending, helping customers to improve their credit rating and offering tools alongside their credit card to help them move forward with credit. BIP is a relatively new product. It's a purely digital product using Apple Pay and Google Pay technology, but without the physical plastic being required. This enables customers to get instant access to credit without having to wait for a physical card or PIN, with the additional benefits which come with Apple Pay and Google Pay, such as unlimited contactless transactions. We also issue Amazon credit cards, again offering an instant line of credit by providing customers with a token into the Amazon account immediately, which allows them to make use of the spend and buy purchases without having to wait for their physical card to arrive. On our new pay product, we partner with AO, an online electrical retailer. This provides new customers with evolving instalment credit options with no need to take out a credit card. Hopefully I've provided you with a flavour of NewDay business and the scale at which we operate. Now, I appreciate there will be people at this summit that may have no experience of financial crime fraud, and therefore I'll go into a little high-level overview of fraud at NewDay and how we manage it. We typically look at fraud in three areas: application, transactional, and first party. As mentioned previously, NewDay accounts for a large proportion of new applications in the UK, and this makes us an attractive option for fraudsters. Fraudsters will obtain genuine victim details through numerous methods, such as from the dark web, social engineering, or even as simple as using family member details to obtain credit fraudulently. Transactional fraud is where a genuine customer's details are misused by a fraudster. This could be in the term of lost and stolen, card not received. So this is where the fraudster will interact or receive the card whilst in transit. Counterfeit is less common in the UK, but still see instances of counterfeit transactions overseas where chip and PIN isn't prevalent. Account takeover. This is where the fraudster will change details on the account, either through servicing or via the contact centre, to then change things like the address so the cards can be delivered to the fraudster's address, but they'll often change the email and telephone number on the account as well, to make sure no suspicions are raised with the genuine customer. And the last but not least, card not present. This is the most prevalent fraud loss in the UK, either through e-commerce transactions or mail order, telephone order transactions. This typically all ties back to data breaches where credit card details have been stolen and then used fraudulently. As I mentioned, we process in excess of 10 million transactions a month. So this is like looking for a needle in a haystack. The last fraud type on here is first-party fraud. This is where the customer commits fraud against us. It is typically in the form of spending against uncleared funds or taking out the product with no intention to repay. For payment reversals, these could be customers that have been with us for several years. Through payment abuse with no protection, customers could get away with multiples of their credit limit. As you can see, I've illustrated this as a circle, as learnings from each of these fraud types help us to mitigate fraud moving forward using the intelligence gathered throughout the life cycle. Now, I'm not going to go into a great deal of detail here, but I wanted to illustrate that like most other credit issuers in the UK and across the world, we use multiple platforms to detect and prevent fraud. We use a layered approach as there isn't a single fraud system which cuts across all fraud types and identifies all types of fraud. We profile devices from where applications originate using threat metrics. We profile the email provided on the application form using email age, and we also profile the phone number provided on the application form using telesign. This is in addition to some of the more traditional credit reference agency data, which is used within our application fraud decisioning. Any high-risk applications are currently referred out to our fraud investigation team to review. They will use a number of different tools and products to reach a decision on whether the application is genuine or fraudulent. Within the transaction fraud space, we again use a number of systems which profiles the customer's spend and behaviours. This, in conjunction with rules developed internally, provide us the ability to decline transactions where we suspect fraud. No doubt, many of you will have experienced this with your own banks, whether it was a result of the bank identifying fraud or where they believe the transaction was not undertaken by you when in fact it was you, and therefore a false positive. Again, as mentioned previously, we are processing in excess of 10 million transactions per month, all of which will be processed through these systems in real time. For first-party fraud, we take a slightly different approach to identification using internal behavioural information, plus we continue to screen our customers against external databases to establish whether the customer has gone bad with one of their other lenders. Just to reiterate, we use many different systems across the lifecycle of fraud, all of which feed into our internal data warehouse for analytical purposes. This is a relatively simple slide, but it illustrates our previous approach to fraud investigation. Whilst working a case, you can see that the investigators are all working in silo. They were gone into all of the systems previously mentioned, in addition to our core account management system, to see if there are any links to any other cases or accounts. This proved to not be effective or efficient, and often things get missed as you do not see the full picture. Working in silo also means you do not accurately identify new and emerging fraud trends or threats, and therefore do not take swift action to mitigate the threat. We needed to be more effective in our management of fraud to identify trends and take proactive action to protect our customers. Since the implementation of TigerGraph, we now take the opportunity to pass all of our data from all of the different systems and platforms, and which in turn drives actionable intelligence, which we can use proactively. You will see I've listed many of the systems we use in application, transactional, and first-party fraud management. This is in addition to other data sources we have, including known frauds, account data. Remember, we have nearly 5 million accounts. All of the IVR and e-servicing interactions, digital wallet data. I could go on, but it just wasn't enough space on the slide to include all of the data sources and systems that we have available and we're currently passing to TigerGraph. Rather than an individual fraud investigator going into all of the systems manually and trying to track any links, we can now do this in an efficient and effective manner since the introduction of TigerGraph. Our fraud investigators, in addition to our fraud strategy and analytics teams, have access to TigerGraph. Due to the obvious data protection issues, I have not used real-life examples. The TigerGraph pictures are just for illustrative purposes only. Now, by passing through all of the data mentioned on the previous slides, we can take early intervention by being intelligence-led. We are now more effective in taking proactive action and protecting our customers who we believe are at risk by blocking their card and issuing them the new one before the fraud occurs. We use TigerGraph to help collate meaningful data which can be shared with law enforcement. We've seen a significant rise in the number of cases we have referred to law enforcement since the introduction of TigerGraph. It enables us to share information in a way which clearly articulates links between accounts, such as by the bank account, the telephone number in the IVR, debit card payment, email address. There are many I could go on. This also allows us to share intelligence with our peers in the UK, so we can help drive down fraud across the industry. So why did NewDay choose TigerGraph? First of all, I wanted the team to be driven by intelligence to help us be proactive in identifying fraud. even before it happens. For me, graph analytics was the obvious choice, but it's been some time since I last used graph analytics. My team went out to see what was in the market. We conducted a proof of concept with a short list of 3, which included TigerGraph. TigerGraph come out on top in comparison to the other 2 competitors. The reasons that we chose TigerGraph: scalability. I've talked a lot about the systems and the volume of data, and this is something that's been easily handled by the TigerGraph solution. Running queries is relatively quick, considering the sheer amount of volume of data sitting behind. Simplicity. Even before we had any formal training, the team quickly and easily started to navigate the system and started building queries, which immediately started to drive benefit. It was also simple to implement in conjunction with our internal IT teams. Analytical capability. It was easily integrated with our analytical capabilities at NewDay. With the huge amount of data we own, we're able to connect multiple data points that were not possible with relational databases. This enhances our current fraud tooling. Flexibility. It enables us to ingest various different data sources easily and use this to drive our fraud agenda. It is easily used across the analytical team with strong analytical backgrounds, but also with our investigators who have very limited analytical capability. Throughout the proof of concept, through to us being a live customer, the support from TigerGraph has been excellent. They have helped us through every stage of the journey to ensure that we'll be a success at NewDay, which I'm pleased to say it has. I'm extremely happy with the direction of travel with regards to the fraud management at NewDay, and TigerGraph is a component part of the reason for this. Now that is the end of my presentation. Therefore, thank you for listening, and I hope you enjoy the rest of the summit. Thank you.
Thanks a lot, Danny, for that wonderful session. We have questions. Please keep teeing up your questions. I promise I'll get to them in a moment shortly. I wanted to ask a few questions of your, that a lot of questions have come in. So I'm going to go ahead and ask a few questions of your, if you can take them now, and
Yes,
then
yes.
we'll also do additional questions at the end. One of the questions was, you mentioned the model PinSAGE. How has the accuracy of, been improved from the previous approach to the one based on GraphSAGE at Pinterest? If you can share any details on the performance and accuracy improvement related to the PinSAGE model.
Yeah, so the first, basically the recommender system we had before was based on collaborative filtering. Also, it was graph-based recommender system that used random walks. The system is called Pixie, and there is also a research paper published around it. So that was the baseline that we had, and so the way it went was first there was a kind of an offline Hadoop-based system. Then Pixie as a real-time system improved, 30+% in terms of engagement over that. And then with GraphSAGE, the implementation we use at Pinterest, call it PinSAGE, it really allows us to do end-to-end training. So it's much more flexible. It allows us to optimize for different types of actions. It allows us to optimize for different types of content. So it is much more widely applicable. It allows us to kind of drive user traffic and user actions in different ways. It also allows us to apply this not only to pins, but also to ads, to products, to newly released idea pins, and so on and so forth. So and the order of magnitude in terms of performance lift was also kind of double digit, and kind of north double digits. So wow. It was a huge success, and this is now the default technology that we are using at Pinterest.
That's incredible. Thank you, Dr. Leskovich. And I will have more questions for you, but I want to announce the third keynote speaker for today, Matt Teixeira. He is the Senior Vice President, Enterprise Data Solutions at Warner Media. A little bit about Matt. Matt joined Warner Media in 2020 to head up Enterprise Data Solutions and is responsible for data engineering, platforms, operations, and capability development across all brands and divisions, which includes Warner Brothers, HBO, and Turner globally. So prior to joining Warner Media, Matt was VP of Data Product Development at Xandr, which is the ad tech division of AT&T. And he has a long storied career there. At 15 years, he has held various positions spanning across data products, big data, marketing, advertising, analytics, and insight. But without further ado, let me ask Matt to share his screen and talk about how Graph Plus AI will transform media and entertainment. And after that, we'll be back for Q&A. I have questions from the audience. I will ask those, and we'll have a nice little chat here. So with that, let me hand it off to Matt Teixeira from Warner.
Thank you. Appreciate it. Can you hear me okay? I know I've swapping from all the different web conferencing tools.
Yeah, we can hear you loud and clear, Matt. And if you want to share your screen video, you can. Otherwise, you can speak.
It's not letting me, but it says you can't start your video because the host has stopped it. But I don't have any material. You'll just see the ugly mug of mine.
Oh, okay, no problem. Yeah, see if you can start it now. Otherwise, we can deliver your remarks verbally.
Yeah, it's still giving me a block.
Oh, here we go. Let me try to do this. Okay, go ahead, Matt. Sorry.
No worries, it's still not working. But hey, in the interest of time, I'll try and click it along the way and see if it unlocks. But we can jump in. So first and foremost, thank you for the invitation here to speak, and I hope everyone's enjoyed the summit so far. And I know doing these things virtually aren't nearly as exciting as meeting people in person and being live. So hopefully everyone's hanging in there, and I'm sure the next one of these that are done will be in person, because I think we're seeing the light at the end of the tunnel. But again, thanks for the invite. So I'll spend a little bit of time talking about some of the shifts we're seeing in the media and entertainment industry, in really how these shifts are requiring the use of more advanced technologies to address some of the challenges that are presented with these. And if we look at this, what we're seeing is a lot of these shifts are positive with placing the consumer front and center. But these shifts are also resulting in an explosion of disparate data signals at an unprecedented level, and the amount of complexity around data management, especially in an enterprise level, has been something that's been challenging. I would say, what's required for us is how do we harmonize and synchronize these signals to enable the most value for not only for the customers and consumers first and foremost, but drive positive business outcomes. That could be driving cost efficiencies as well as revenue growth along the way. So I'll talk about kind of three core themes or fundamental shifts that we're seeing, and kind of discuss where we're seeing the use of graph technologies and machine learning and AI to address these. And the three themes, really, in my opinion, kind of are the embodiment of the 3 V's of big data, for those familiar. So, volume, variety, and velocity of data generation, and where these tools are appropriate to address these. So kind of the first theme would be the shift in consumer behaviors and content consumption. Second being demand for differentiated experiences by consumers. And a third being an increased focus on consumer privacy in protecting the rights of individuals around how data is used for various purposes. So kind of double clicking into the shift in consumer behaviors and content consumption, we live in an era where there's more options and ways to consume content in the greatest kind of library and variety of content than ever before. And with that comes quite a bit of fragmentation. in the ecosystem. And so, as we all know, as being consumers of content, there's multiple modes or modalities and channels. You can consume linear TV, you can consume content digitally on your mobile device or your PC, in a web environment or an app environment, over the top delivery of content. Then there's multiple platforms, and I'd be remiss if I didn't have a shameless plug for HBO Max being one of those top platforms. But you've got Roku, Amazon, Apple, Samsung. It really, the dichotomy of choice is alive and real. And the type of formats of content, live, video on demand. You've got audio and podcasts, and then various service offerings where you've got different models that are subscription based, some are ad supported. And with just in this area, the challenge of connecting user behavior across all of these dimensions is extremely difficult, especially from our perspective at Warner Media, when we have such a large portfolio of brands and content. And later I'll talk about kind of some of the trends and things where we're employing with regard to addressing this challenge with graph technology, machine learning, and AI. In addition to just the modes and variety of content available and ways you can consume it, there's the need to adhere to various data governance requirements to enforce the appropriate application and use of that data. And these vary quite a bit. They vary by partner, like our distribution platforms, our partners and platforms. They vary by brand. They vary by geography. And what we're also seeing is an increased desire for data ownership and generation, and that being a strategic competitive advantage. So the need to establish and generate persistent first-party identifiers so you can maintain continuity of consumers across experiences, brands, properties, etc., as well as the additional need for metadata and how you can use that metadata to further contextualize experiences for consumers and really elevate the experiential nature of a service offering. The big challenge here for us is this also requires the use and integration of a combination of first and third-party tools, and really with the main objective of the unification of the disparate signals so we can establish that 360-degree view of the consumer. And from our perspective, that allows us to enable advanced insights and analytics that are much deeper than before, data-driven marketing approaches, unique advertising, and consumer experiences. And so when we think about the demand for differentiated consumer experiences, really with personalization and these curated experiences, there's an expectation from consumers for these. And it's, from a consumer perspective, it's like, my likes and interests, what I consume, and please put forth an experience that is meaningful and enjoyable when using these products and services that's unique. And that requires not only using data that's generated within and on our platform, but as well as off platform, where we can gain a much more rounded understanding of consumers' likes and interests beyond what we just observe with kind of direct interaction and explicit actions taken on our platform. In addition to that, with an ad-supported model in certain areas, how can we reduce ad loads and ad fatigue? The age-old, it goes to commercial break and you see the same ad over and over and over again. But how can we now use the behavioral signals and engagement and contextual data to adjust ad formats, the placement, the frequency in which ads are delivered that are distinct and custom to an individual's user preferences, in which ultimately allows us to retain these consumers. I think we can attract consumers based off of content, but really enhance experience is what retains them and wins them over. And again, like just between these two themes, you can imagine the amount of different data signals that we have to pull together. The third theme, in terms of increased focus on consumer privacy protection, is a good shift, but it also comes with even more disparate data signals that need to pull together. So we're seeing governments and legislators leaning in, legislation being passed. We've got CCPA, CCPRA soon, GDPR, VPPA, name your 4-letter acronym. All of these come with kind of varying degrees of compliance requirements around data collection, transparency, enforcement across various geographies. And the number of what I call kind of points of presence where these consent signals are collected is fragmented as well, but also bespoke to certain uses and purposes. So from an advertising perspective, we have governing bodies and industry standards such as the Digital Advertising Alliance, the DAA, ad choices, you've got on-device consent, you've got privacy policies and websites set up to capture consumers' privacy protection in elections specific to a particular brand. And we're also seeing the elimination of third-party cookies and IDs that have been used for decades to really track consumer behavior across sites. And we're seeing this shift to an opt-in paradigm, and the ability to leverage device IDs is moving in where consumers have to give explicit consent. So yet another piece of data that we have to honor and enforce to make sure we're good stewards of collecting and using data while we deliver differentiated experiences and content wherever possible. And so these shifts, one might ask, okay, what does all that have to do with graph technology, ML and AI technologies? And it really comes down to those are the tools that are really required to establish the appropriate connections, the intersections, the relationships within really like a rat's nest of data that on its surface seem extremely disconnected. Additionally, we need to employ predictive and inferential-based techniques that are informed or influenced by the amalgamation of these disparate data sets. So as we pull more signals and variables that models may predict or determine are more indicative of certain outcomes, these signals really, it's kind of the saying, the sum of the pieces is greater than the individual parts. But really at the center of a lot of this is, from our perspective, is a core identity graph that really gives us a firm understanding of a household, device and individual usage data, behavioral data, where we can deliver these experiences, as well as pull through all of the appropriate consent elections and enforce those. And so from an identity perspective, there's some things that are known, but there's a lot that are unknown. And the ability to use ML and AI to impute inference scores using behavioral data to disambiguate some of the ownership and assignment of devices to people and people households is key, as well as maintaining lineage on transient account and subscription relationships. So for example, a consumer may sign up for a limited trial on a website, provide a piece of information or PII, but may not sign up for said product for months. We leverage graph technology to thread and tie those events together and maintain that continuity and lineage throughout the kind of relationship journey with a consumer. And as I mentioned, we also look at and pull through governance and consent enforcement within the graph. So this is like adding elections as attributes to vertices or edges from various sources, as described earlier, since there is quite a bit of sources that we have to pull from to enforce. And then we're seeing a lot and doing a lot with metadata generation and using deep learning techniques that really in the content recognition space, you think about text, audio, visual recognition, where we can almost create a microscope of content metadata beyond the kind of generally available sources today we see out in the marketplace. A lot of focus on personalization and recommendation. So again, pulling that ID spine is decorated with all of those behavioral contextual engagement signals to deliver a much more personalized experience and recommendations around content and certain services. We see it also and employ it with supply and demand forecasting. And another interesting one that was unique given the times we're living in is theatrical launches, which theaters were shut down. But as COVID rates started to go down, being able to develop predictive models that take in the COVID information around rates of infection tied to consumer behaviors in certain localities and geographies to understand as theaters and exhibitors start to open up, which theaters make the most sense for us to release some of our new theatrical releases. So just kind of a highlight. I think the shifts were important to understand how we're approaching these very challenging problems with this kind of proliferation of data using graph technology and ML and AI. And so in kind of closing, I'll leave you all with what I thought was a great way to kind of visualize in my mind. I have a product manager on my team who's like, I look at graph technology as looking at something in 4D versus, say, relational databases or key value pairs are kind of 2D. And I like that because that fourth dimension is really a temporal one, being time. And being able to connect these signals and linkages and relationships over time and space over kind of across these myriad of data sources is key. And I thought that was kind of a neat way to think about graph technology. So I look forward to taking any questions in the roundtable that's to follow.
Excellent. Thank you, Matt. And that was excellent presentation. Thank you for doing that. My first question is for New Day's Danny Clark. Danny, what kind of a performance improvement have you seen with graph compared to the prior way of fraud detection in terms of matrix? Anything you can share with us?
In terms of metrics, it's on our fraud preventions. So we've seen a significant increase in our fraud preventions as a result of us being proactive in using the data. So that is in an increase in the region of kind of 10 to 15% versus what we were seeing previously. We were very much in our infancy of using Tiger Graph, so I'm absolutely confident that we'll see that improve further.
It's incredible. And next question is for Dr. Leskovich. The example that you mentioned about drug interaction regarding side effects of using multiple drugs, what kind of, after that learning it through GraphSAGE model, what kind of recommendations are provided back to the patients, or how is it used in terms of output?
Yeah, great question. So the way you can think of it is, right, that basically now for any pair of drugs, we can predict what side effects might occur. So you could imagine basically having almost like a recommender system where a doctor would say, here I have a patient on these drugs and I'm considering adding this additional drug. What kind of side effects may I expect? And what is the benefit of our approach, right, is that we can make these predictions for pairs of drugs that have never been prescribed in the past. This means that for any pair, we can make this prediction, which means the system is really, really useful. And also, if you think about it, how we learn about these effects today is that basically doctors by chance prescribe drugs together. You know, something goes wrong. Usually it takes, I don't know, half a year for the patient and the doctor to figure out that this is actually caused by the drug. And I'm sure, you know, some of you here in the audience went through this experience, and we got a lot of emails, people saying, hey, I went exactly through this, and now in your paper, I see exactly this prediction. You know, it took us, me and my doctor, half a year to figure this out. And then, right, doctors need to report this to FDA. And as FDA collects enough evidence, then they add it to the official side effect list, right? But with this type of system, you can basically do this in real time for any pair of drugs on the spot.
That's incredible. And there was a great session yesterday from Jesper Wang of Technical University of Denmark, who actually shared very interesting insights also of combining graph results, you know, using genomic research combined with the trial results to try to predict things. I mean, this appears to be in line with that. That's great, Dr. Leskovich. The next question is for Matt. Matt, you mentioned identity graph as a central part at HPO and also at Xandr. What type of performance improvement or benefits have you seen? Can you talk a little bit about what kind of benefits have you seen from implementing graph and identity graph at Xandr and as well as HPO?
Yeah, absolutely. I think the key thing would be speed, which I mean exponentially. It was probably I would have to check with the team, but I feel like it's like 50x plus when we're trying to identify relationships that otherwise we were unable to do, or it's extremely intensive in processing, and the speed in which we could surface those connections took much longer. And so I think now what we're looking at is with the scale of Warner Media plus AT&T, we're talking about billions of relationships, and that's really where graph technology has been key in terms of being able to surface those relationships and get to a much deeper level of analysis than we've had previously with traditional, air quote, traditional technologies.
That's incredible. That's a big scale. With that, I'm going to ask my last question of the panel here. And again, we'll start with Danny first. Danny, what are the plans of future deployments of graph? Where do you plan to take this in terms of deployment at New Day? Are you looking at deeper areas in fraud detection, or new areas beyond fraud detection at New Day?
Yeah, there's very, very much an intention internally to kind of grow out Tiger Graph within New Day, so not just limited to fraud. We've kind of showcased the product to our areas of the business, so financial crime, money laundering, and even in our operational areas. I think it's fair to say that everybody within the organisation sees benefit with the tool. But more locally, from a fraud perspective, we're still on a journey to introducing more and more data into the solution to help identify those connections and get to the cases much quicker to prevent fraud. So yeah, plenty of opportunity with the tool outside of our key area, as well as growth in our area.
Wonderful. Thank you, Danny. Dr. Leskovich, at Pinterest and also at Stanford Research, what are the additional use cases that you see? What are the features for the GraphSAGE? Where do you see it headed?
Yeah, that's a great question. So what we are working on is special use cases around fraud detection, security. So in this kind of high-speed streaming networks, temporal networks, definitely recommender systems, and kind of holistic understanding of a user, for example, is one of the research areas, as well as just scaling this up and making these models more robust and kind of easier to use, so that we can kind of democratize their use to the wider community.
That's wonderful. Thank you. And I look forward to seeing more updates from you and Stanford and Pinterest on that. Matt, you have the final word. Where are we headed with identity graph, with recommendation engines, and everything else that you're doing wonderfully at Warner Media, at HBO, at AT&T? How do you see this? What's the future for graph inside these organizations?
Yeah, on the Warner Media side, we're really looking to extend this into our media supply chain. We've got 3 legacy catalogs of content across WB, HBO, and Turner. All which can carry similar titles, which requires deduplication and a generation of a single ID for that piece of content that can be pushed into our platforms and allow us to then decorate that with additional metadata and converge our identity graph with what we would call our content spine. So I see the next immediate evolution for us is moving this into the media supply chain piece and elevating what we do with content metadata. And I believe, on the AT&T side, I know they're eyeballing some fraud approaches as well with graph technologies. But my immediate focus is now on how do we bring identity and content metadata closer together, and rather than 2 disparate spines, but one that can live together and get us closer towards the movement of kind of the notion of a knowledge graph.
That's wonderful. Thanks a lot for joining us today, Dr. Leskovich, Danny Clark of New Day, and Matt Teixeira of Warner Media. Thank you for joining us, and thank you, audience, for staying through the Q&A. Additional questions and answers, we will email responses back from the panelists today. Thank you for joining us, and stay with us for a couple of exciting roundtables following this, and also a host of sessions, technical hands-on session throughout the morning and afternoon. So please stay with us. Thank you for joining us, and enjoy Graph+ AI Summit. Thank you.
Thank you.
Thank you very much.